TLS, which stands for Transport Layer Security, is a protocol for securing communication between the client and the server. It is specifically used in the HTTPS protocol. That's what the S stands for, by the way. All right. In this video, we will talk about, obviously, before jumping in the security part of it, we really need to talk about the vanilla HTTP, how these things work, right? And we're going to talk about how HTTPS work, again, bird's eye view. Then we're going to talk about the abundant TLS 1.2. That's the most, I think, the most used encryption out there for the HTTPS protocol. We're going to talk about specifically the handshake before sending the GET request, right? Then we're going to jump into the new version, which is 1.3, which improved a lot of stuff. We really need to talk about Diffie-Hellman. I thought that we really need to talk about this key exchange algorithm. It's a very popular key exchange algorithm, which is used all over, which solves a lot of problems in the RSA encryption algorithm, okay? Which jumps finally to the TLS 1.3 improvement, right? Which is much faster, much more secure. This is coming up, guys, right? Guys, if you're new to this channel, welcome. My name is Hussain, and in this channel, we discuss all sorts of software engineering by example. If you want to become a better software engineer, consider subscribing. Check out the other content of this channel, right? That's it. Let's just jump into the video, guys. So the first thing we're going to talk about is the vanilla HTTP, okay? So how HTTP works. Usually, most of the time, you have a web server listening on port 80. That's what the HTTP protocol runs at. Obviously, you can spin up an Node.js or a Tornado Python app, right, which listens to other ports. But essentially, most ports, when you do HTTP google.com, the implicit port is 80. Okay, what HTTP runs on, most of the time, it runs on the TCP protocol, right? And TCP is a stateful protocol which has knowledge both on the client and server. There is a bidirectionality of this, while the HTTP protocol is a stateless, and it really needs the TCP protocol just to transfer stuff. That's it. So that's why a lot of people tell you, hey, HTTP, you can use UDP over HTTP if you want to, right? You can use anything. That's the beauty of HTTP. It's the stateless. If the connection dies, the HTTP protocol will realize, ooh, my connection died. Let me resume it or create a new one, okay? So that's what I mean by open and close here, okay? When I first want to establish communication like google.com, I open a TCP connection with a server. You don't see this. Usually browsers do that. Your browser essentially does that for you. It opens a TCP connection. Your fetch API does that for you. We talked about fetch. I'm going to reference it here. The fetch API, when you make a call from the browser, right, or any application, even from Node.js, if you use a library like XML HTTP request, right, does the same thing. Okay, so here's that's in a nutshell, right? You open a connection and then eventually you close it. Now, opening and closing the connection really differs based on the version of HTTP. 1.0, it was literally opening and closing connection after each request, right? But they changed that, made it persistent connection. We'll cover that in another video. But open connection, sends a GET request, GET slash, right? Fetch GET slash, and then that's essentially, that means usually the root, sometimes the index.html. What it does is like the server processes this request. If it has enough bandwidth, it's gonna process the request. It's gonna take time processing that request, obviously, guys, right? And then it's gonna send back the headers, content type, text, HTML, and other stuff. Perhaps maybe set cookies, anything, right? There's a lot of headers and the actual index.html and the result, right? And I deliberately added a gap here. This is the latency it took, right? Whether the bandwidth latency, the server processing the stuff, right? You compute stuff at the back end, you query the database. There must be some server latency. You want to minimize this as much as possible as software engineers, right? Okay, guys. Again, guys, when I talk about TLS, I'm going to talk about all that stuff. I am going to reference software engineering part of it. I'm not going to talk about the mathematics of encryption and all that stuff. I'm not good at all that stuff. I'm going to reference videos for if someone is interested in the math of the encryption and all that stuff in another video. Professors do that much better than I do, obviously. Okay, that's the HTTP, vanilla HTTP. HTTPS, how does it work? It is exactly the same. Only difference, port is different. 443. We usually listen to port 443. And again, is not visible, but that's the port that we listen to when we establish communication securely. Okay, so that's the thing. Another thing is like there is something that happens before we send the GET request, which is usually it's called a handshake. And the goal of this handshake is for both the client and the server to agree on a key, which is the symmetric key that will be used to encrypt and decrypt encryption. It is the same exact key on the client and the server, and then you can start asking questions. Now, what is the difference between symmetric and encryption and asymmetric question? That is why we made a video. I'm going to reference it here, the difference between encryption, the symmetric encryption and asymmetric encryption and all that stuff. Why do we have two in general, right? There's always a reason. Okay, I'm not going to go through them essentially, but here it's the same key, right? And it's much faster than the asymmetric encryption. That's the goal of this handshake. Once we have, each one has a key, the client will take that key, take its GET request, lock it. By locking it means encrypting it. So this will essentially become garbage, right? Garbaging out, right? The TCP connection will take that garbage, the encryption. Usually this thing happens on, I would say, the layers that are layer 7-ish, layer 6, right? We talked about the OSI model. I'm going to reference to that. So it's going to encrypt it and then just shove it down the TCP. TCP is just blindly transporting the payload. It doesn't know it is encrypted. It just knows that there's a bunch of bits. I need to transfer it to the server. That's what it did. The client, the server will receive that. It will use the key to decrypt it. It will understand that it's a GET request. It will process that. Look at that. I made it a little bit longer because there is a decryption involved. So obviously there is always a cost, right? Software engineers, guys, we really need to understand these latencies and every single piece, right? That's why we really need to understand this TLS, how it works. At least an overview. You don't need to understand the details, but you need to understand how this is affecting our work as software engineer, right? When we write code, we really need to understand what's going on, right? We can't just we don't really care about what's going on, right? It's just like, oh, this is all black box. Sometimes you need to understand basic stuff. Encrypt the index.html or whatever the response, JSON, anything, encrypt it, send it back. Anyone who sniffs this is gonna get garbage. If they have the key, they will be able to decrypt it. Okay? That's the key. That's the key. Pun. Okay, so got the key and then close it. I put 3 dots ellipses here. That means like it doesn't really close it right after the response. It used to do that in 1.0, but in 1.1 there's a keep alive that send the server will say server, hey, by the way, keep it alive. Please keep me alive. Don't kill me. Right? In general, I like to talk about different software engineering aspects of this thing. TLS 1.2, the most popular thing that is used currently. I'm not going to talk about the previous old SSL stuff. It is completely outdated and is very unsecure. But I want to talk about what is abundant right now, what is used right now, why we should move to 1.3, but let's talk about 1.2 first. Okay, 1.2, TLS, Transport Layer Security, same exact thing. So remember, guys, when we explain the handshake, this is what we're going to talk about. We're going to kind of zoom in to this handshake arrow and then try to explain what's going on here. So when they first designed TLS, they said, we're going to make it configurable. We're going to make it fancy. We're going to make it options. We're going to make the client give options. We're going to make the server had options, always about options. And then what the client did, it says, okay, I'm going to send the client hello. There's a lot going on there. I'm going to talk about it. Now, client hello has a lot of other information. I don't have a space to add all of that stuff, right? In a nutshell, the client says, hey, my name is client. The TCP is already established, but now we're sending the first request, and the first request is the client hello and says, yo server, sup, my name is client, and here's all the ciphers I support. I support for key exchange, I support RSA, I support Diffie-Hellman, I support this, I support that, right? For symmetric key, I support AES, I support DAS, I support this, I support Blowfish, I support all that stuff, right? And it's right, depends on the client, because maybe it's an Internet Explorer, so it only supports old stuff. Maybe it's a brand new Chrome 76. I don't know if there's a version 76, but I just made it up. But in general, it supports more newer stuff. The server will say, sure, looks, you're cool, you're a little bit old, so we're gonna use this encryption algorithm for a key exchange. We're gonna use this encryption algorithm for symmetric key. Here is my certificate, and the certificate is a fancier term for the public key of the server. Okay, it has a lot of other stuff, include the public key of the server, and which will be used, right, by the client to encrypt the symmetric key. So the client will say, okay, you want me to use AES? Sure, I'm gonna go ahead and generate the symmetric key, right? It's not really the symmetric key, it's the pre-master key to generate the symmetric key, but might as well just call it the symmetric key for simplicity. So I generate the symmetric key, and then here's what it does. It will use the server public key, lock it up, lock the key, and send the key through the server, right? It will send it over, right? And that's essentially what the RSA model works here, okay? So it's using RSA in this case. Locking the symmetric key, sending it in the network, and that's really bad, right? We're gonna talk about it. Even you're gonna say, hey Hussain, this is encrypted, why do you care? Right, we will talk about that, right? It's encrypted, but you're sending the key. If someone got this, somehow they encrypted this, all the chat, they just decrypted the whole thing, right? If someone got the private key of the server, they will immediately get access to everything. But nevertheless, they got the private key, they got the symmetric key, the server got the key now, okay? Now now it have the server, both of them have the symmetric key. They take it up, and then the server will finally says, I'm finished, let's go ahead and start communication. So you can already see that we reach the state that we want. Both of the server and client have the symmetric key. They will start encrypting, send the GET request, encrypt, send back the response, and that's it, right? So you can see, guys, already that there's the problem, right? The problem is we're encrypting the symmetric key or the pre-master key and sending it over. And that's a problem, right? That's the problem with 1.2, okay? That's one problem with 1.2, because you're giving insecure key exchange algorithms, okay? Like this one. You're allowing me to encrypt the key and just send it over. If someone managed to get the private key of the server, it is over, right? So you're gonna say, oh, how can you get the private key of the server? It happened before, Heartbleed, right, guys? Like OpenSSL, like there was a problem with the server, and this unpatched OpenSSL, some people were able to pull information from the server, and they were able to pull the private key of the server. So it happens. It's not as easy, but people could do that, okay? That's why you have essentially the encryption algorithm, the exchange that we're going to talk about next, which is much more secure, okay? Another problem with 1.2 is, look at that, guys. What is this? You want me to keep chatting in order just to send a GET request? There's a lot going on. Yeah, 4 round trips is not simple, right? This is going back and forth 4 times before I can send a single byte to the server. That is actually meaningful. So it is slow. Yes, it is slow. Slow, insecure. Okay, and the insecure, there's an asterisk there because it depends really on you. That's back to the options, the abundance of options that we give in 1.2. Diffie-Hellman. Let's talk about that. There's a problem with the key exchange algorithm, especially RSA, which is having the public key and having us encrypt the symmetric key and sending it over, even if it's encrypted and nobody can decrypt it except the server. If someone got that private key, people can essentially decrypt the entire communication. So these two guys came up with a smart idea to send information about the key, but not the actual key, and let the parties essentially generate the key for them. And here's the TLDR of this. There's a huge mathematics there, right? I'm gonna reference a video here that a professor did on the Diffie-Hellman, the math and the actual algorithm. But that's what the basics of it. So you have three keys. You generate a private key, right? A red key and a private, and the blue key. Let's say these are private. These must not be sent by any means through the wire. You don't send these. Okay, you only send the public key. So there will be three pieces of keys here. Okay, if you combine these, if you manage to have all the three, you get your symmetric key. That's the goal of this. Adding the private, the blue and the red and the pink key will give you the private key. That's the goal of this. However, the blue key is the first party. It is private. The red key, it is the destination part, which is the server, or yeah, that's also private. And there is a key that is here that is also public, and that's okay if we send it over the wire. Okay, so private, public. Okay, got it? Combine them all together, you get the private key. Okay, the symmetric key, the key that we want, the secret key. Here's one more other information. Combining the blue and the pink, which is the private and the public, together can be public. That is okay to send it over the wire because it is unbreakable. This algorithm, the Diffie-Hellman, if you combine those together, there's no way to break. Well, there is a way, but it's very expensive to break those two together. So we said, okay, blue and pink can be sent together because if the attacker can sniff those, they won't be able to break those and get the blue key. Again, this shouldn't be alone. This shouldn't be discovered. The red alone shouldn't be discovered. Same thing with the red and pink. Combine them together, it's unbreakable, right? And could be public. With that said, let's repeat it a little bit. Private, public, and private. Okay, this is the client. This is the server. And this is the public key that usually the client really generates and sends it over. Combining these together is public and unbreakable. Combining these together is public and unbreakable. Combining the three will give you the private key. Okay, so with that said, we are ready to talk about 1.3, guys. Okay, here's 1.3 does. It says, guys, enough with these options. Okay, you get no options from me anymore. No options for you. Come back 1 year. What happens here is the client will always force the server to communicate over Diffie-Hellman. Okay, this algorithm that we're talking about. It will be given choice to which symmetric algorithm to use. Okay, but key exchange, no. Just Diffie-Hellman, ephemeral Diffie-Hellman, which we will going to talk about after this slide. But in general, that's the blue key. Nobody can see it. The client generates that, and it also generates the public pink key. Remember, this is public. Okay, it generates two keys, the private and the public. Here's what it does. It sends over the public key. Who cares? You can, right? Aladdin, remember? Aladdin can just sniff it and then just steal it. That's okay. And then it merges the public and the private key together and then send it over. Again, we don't care. Remember, this will be a number essentially. Merging these two will be a number. This will be a number. All these are just prime numbers, and that's why mathematics is very important in computer science. Okay, so merging these together, that is okay, right? This is alone, that's okay because that's public. These two are public. This guy is not. Remember, merging them together, you cannot unbreak them. So they are together, they can be sent. Okay, so the server, what it does on the other hand, it generates privately this key. Keep it very secure. Temporary server key. And then what it does, it takes these two keys, add it to the red key. Guess what, guys? We just got the golden key. That's it. We got it. One round trip. We got the key. One round trip. We got the symmetric key immediately. Well, again, this is not the symmetric key. This is the input to the algorithm that gives you the symmetric key. But essentially, it's almost the same. Okay. We got the key, guys. How do we get a client? Remember, the client doesn't have the key. The client needs the red key to merge these two in order to complete this cipher, right? So we cannot send the red, unfortunately, just by itself, right? That would be bad. Sending the red, if you send the red, the Aladdin will Aladdin, by the way, this is just from the encryption. From the encryption and asymmetric video that we made, right? So instead of always Alice and Bob and Charlie as the hacker, we just made it Aladdin for some reason. Okay, so Aladdin will pick up the name, right? We'll pick up the red key and then combine it, and he will just have that key, dude. So that's bad. So what it does is it will take that public key, the PIN key, merge it with its red key. Remember, it has that, and then send over those two. That's cool, because those two together, that's okay, and they are unbreakable. Remember, they are public. It's okay. If the Aladdin got hold of this and this, he will not be able to break them and get the yellow key, right? Because he's gonna get what? He's gonna get two pink keys, and it's gonna be messy. It's not gonna be possible, right? Send it over. Now the client will have these two. It has the blue key. Combine them together. Got the golden key. Done in 2 round trips, guys. TLS 1.3 is done in 2 round trips. It's much more secure, right? It's much faster because I don't have to do all this negotiation anymore, right? And then encrypt using the fancy golden key. Get requests, similar thing. Send back index.html, and we are done. How coolish is that, guys? How coolish is this? With that said, let's finalize this video, guys. So what did we talk about? We talked about vanilla HTTP, a little bit about 1.1 and 1.0, 1.1, the difference. We know that it's an underlying TCP connection. It's a stateless protocol. It's an insecure protocol, but it's damn fast, right? But we really need security, right? So we invented HTTPS. Really, anything that can encrypt us underneath, we're good to use. So SSL came into the picture, right? TLS 1.1, 1.0, 1.2 came into the picture, right? And then start encrypting HTTPS. And then we talked about TLS 1.2 handshake, right? Talk about that stuff. We know that is secure, cool. It's better than the previous, but it's very slow. There's a lot of going back and forth, guys, right? It's also insecure because it's using RSA, and if someone got hold of the private key of the server, they can encrypt the channel, and they can see all our, the chat that we are discussing. Okay, Diffie-Hellman, we talked about this beautiful encryption algorithm. Okay, well, the only thing we didn't mention is the ephemeral. I can't even pronounce it. Okay. Right? English is not my first language, guys. Diffie-Hellman, ephemeral Diffie-Hellman is when the blue and the red key is essentially temporary. They are just generated every time, right? You don't keep them. You destroy them and regenerate them every time, right? And that's essentially the ephemeral in a nutshell. 1.3 improvement we talked about is how fast, how cool, how secure is 1.3. All right, guys, this is the end of the video. Hope you guys enjoyed it. Give this video a like if you like it. All right, subscribe, and I'm gonna see you in the next one with more coolish software engineering videos. Stay awesome.